Today I'm going to talk a little bit about sex-linked traits and show you how to do a Punnett square for traits that are sex-linked. Sex-linked means gender-linked. They are traits that are found on the gender or sex chromosomes, which are your 23rd set, and they tell you if you are a boy or a girl. If you have an X and a Y, you are male, and if you have an X and an X, you're female. So if you take a look here, your biological mother had two X's, and your biological father had an X and a Y, and that's the same for all males and females. So there's a 100% chance that you're going to get an X from your mother because that's all she has to give you. And then there's a 50-50 chance that you'll get an X from your father and a 50-50 chance that you'll get a Y from your father. So you get an X from your mother, and then if your father gives you an X, you are a female because you have two X's. And if, well, not if, because you got an X from your mother for sure. But if your father gave you the Y, then you are an XY. You are a male child, a boy. This is an image of the actual sex chromosomes. And on the left here, we have the X chromosome, and on the right, we have the Y. And as you can see, the X is much larger than the Y. But don't worry, boys, that doesn't mean anything bad. It just means that you're more likely to express traits from your mother on these chromosomes if you are a male, because there aren't very many traits on the Y chromosome. So does that mean that girls have twice as many traits? Well, they have more chances of getting a wider variety of traits, but they don't express double the amount of traits. They only express half. Just like any other chromosome set, you only express half of the traits. And so half of them are going to be turned off if you're a female. The other X won't be expressed. So what would be an example of one of these traits? Well, color blindness is a different way of seeing color, and this is a trait that is carried on those gender chromosomes, the X chromosome. So if you inherit the color blindness trait, which is recessive, it means you can't really tell the difference between red and green. So normal picture, this corner is the normal vision picture. And then these other three show different variations of what it might look like if you have color blindness. So basically, reds and greens either all look kind of red or all kind of green or somewhere in between. Now let's do a Punnett square for color blindness and see what happens. So I'm going to repeat again that color blindness is a recessive allele, and a lot of the traits that we'll look at on these sex chromosomes are recessive alleles. Another example would be hemophilia, which is a blood clotting disorder, and most of the time we're going to focus on recessive alleles, which means that if you're a female, you could get a dominant allele from one parent and a recessive from the other and still turn out fine and not express one of these things. But as a male, you only get one X. So if you inherit one of those recessive alleles, that's kind of it. You're going to express that recessive trait because your Y doesn't carry really anything. It doesn't carry a dominant, it doesn't carry a recessive. It's sort of a placeholder. So let's take a colorblind male, which is noted XY, and then we also note the color blindness with a C, and you can use a superscript or you can use a subscript, but somehow you have to mark on that X that it carries that recessive color blindness allele. Then the Y goes second. Now you're going to put the Y in there, but once again, it's a placeholder. It doesn't really carry any trait whatsoever. This is a normal female. She has a genotype of XX, and she doesn't even carry the color blindness allele. But I would like to point out that she could potentially be a carrier for color blindness and have that recessive color blindness trait attached to one of her X's and still have normal vision because it's a recessive trait. But in this case, they're telling us that her genotype is just normal X, so that's what we've got. All right, I'm going to start by putting the color blindness trait on that X for the male here, and then my Y here as a placeholder. And then my normal vision female, her X's go along the side here. And then you go through and complete your Punnett square the normal way. I'd like to note that this is the recessive X, so I'm going to put it second. However, if you have an X and a Y combination, the X always comes before the Y, no matter what, even if that first X has a recessive trait on it, because it's really the only one, but it always goes first. I don't know why. Okay, so here's my Punnett square. Let's look at the results. I've got a female with normal vision. She's a carrier, which means she carries the colorblindness trait. She has it in her genotype, but her phenotype is normal vision. She does not express it because it is recessive, and she's got this other dominant X, so she's not going to be colorblind. Normal vision. This is a male, and he also has normal vision. This is another female, and she's a carrier but has normal vision. This is a male and his normal vision. Now, once again, remember, it doesn't mean there's 4 kids necessarily. These are probabilities, so it's a 25% chance of all of these things. So let's look at the results. What percent are colorblind? 0%. What percent have normal vision? Well, 100%. What percent of males are colorblind? 0. And what percent of females are colorblind? 0. Those are easy answers. So that's how you would do a Punnett square for a sex-linked trait. Let me know if you have any questions in class.